Now, next thing, we want to build one translator. And how we can do this, well, say we have German sentences. We want to transform them into English translation. And, well, obviously, we need to have a sequence-to-sequence model, right? And this should be encoding, decoding, right? What do you choose as your encoder? What it would be? Should it be a CNN? Should it be an RNN? What it should be? What is it? Just just choose. RNN, obviously, right? Because you have a sequence of tokens, you want to just process them. Obviously, you need to have a kind of sequence model, so RNN makes sense to be chosen. And your decoder, this is your encoder. Your decoder should be also an RNN because, again, it wants to start from something and wants to generate some text, right? A sequence of tokens, so it should be also an RNN, right? Now, one thing that you should pay attention here is that there is no need for your output sequence to be of the same length as your input, right? One long sequence might be translated into a short sequence and vice versa, right? So this is how your encoder looks like. It's going to start from some hidden state, initial hidden state. It's going to get the first German token. It's going to process it. It can give you one output, but probably right now you don't need it. We're going to use it later, but right now you don't need it, right? Because you don't want to talk about the first token, actually. The thing that you need is your hidden state, right? You get your first token process, you get your first hidden state, right? That hidden state, along with the second German token, goes inside the network again, and it's going to give you the next hidden state, right? And it keeps on going till it's over with the complete sentence, right? So the whole German sentence has been processed. Now, this last guy, HT, your hidden state at the last time step, this is supposedly carrying information about the whole sentence, right? So it's saying that this is a sentence, maybe in the present tense, it's talking about this, and this is the idea of the sentence, right? Now, you're going to take this HT, the last hidden state, and you take it as your initial state for your decoder, right? Because your decoder is supposed to start speaking English, but about this, right? Same idea, right? So you're going to give this guy to your decoder. What's going to happen? Your decoder is going to see the first hidden state with a start, right? So you're going to say, start speaking, and you're going to say, OK, this is present tense, and it's talking about this, so maybe the first word I should say I, right? Then you're going to get the first token. It's going to carry or pass that token in time to the next time using the same hidden state. Now, S1 is going to say, OK, this German sentence was S0, and you said the first token, Y1, right? Now say the next token. And you're going to keep on going till it's over, right? Now, this sentence could be of different length, right? And you don't care, your architecture is going to handle it, right? So once you process the whole German sentence, then you give it to your decoder. The decoder is basically a language model. And you're going to start speaking, and hopefully it's going to stop when it's needed, right? Everybody's clear? So this is how you're going to do it. Then when you do want processing at the encoder right now with this very basic architecture, we are not going to take a look at the output, right? We don't need the output right now, right? The only thing that is just encoding the information for us is essentially the hidden state, right? The output, we don't need it, right? Right now, we're going to ignore it. Now, at the decoder, what is going to happen? We are going to sample the output every single time, right? The input goes in every time. Then you're going to sample the output. One thing that could happen, like ideally, is that you actually don't give any input at all, right? You can do that. Because all information that you have is inside the first hidden state, right? You can give S0 with no input, right? It's going to say the first token. Then again, that one is going to give you the next hidden state, right? S1, and then you generate the next token, and so on. You can think like that, but you might guess it's like you're being too stingy to your decoder because it needs some information what you have set up to this point, right? So it makes sense that, for example, if you have sampled the first token, then you give the first token as the input to the second time step, right? You can do that as well, right? If you do that, it might help your decoder to speak more fluently and better, because in addition to the hidden state, it has some extra information, which is what you have set up to this point, right? What was the last token, right? It can do that. So, yeah. Now, if you want to do the training, obviously you're going to do it all together, right? So you start with your German sentence, you give it as the input, you process it, you get your last hidden feature, right? You give that hidden state as the initial hidden state of your decoder. Again, you process it till you get the output. And once you got the output, what you do, you try to look at the English translation, which you have inside your data set, and you minimize the cross entropy between the tokens at the output and the token inside your data set, right? You compute the loss, you minimize it by backpropagation, and you keep doing it for lots of German English translations, right? And then if you have done it on a large enough data set, then gradually it starts to translate any German sentence into English. Everybody's cool? Right? So that's basically what we did. So if you want to backpropagate, you're finishing here, so you compute all the losses here, right? And then you can backpropagate. When you backpropagate, you're going to compute the gradient with respect to the hidden state at every single time. So obviously, you are able to compute the gradient with respect to the hidden state at the beginning of the time in the decoder, right? That one is the gradient of the loss with respect to the output or the last hidden state of your encoder, right? So you pass it here, so this is going to be the gradient with respect to HT, and again you backpropagate through time till you get all the gradients, right? And now you have the gradient with respect to the weights of the encoder and decoder you're going to update, right? Everybody's cool? Questions? Okay, cool. Now, let's see one specific sentence, and I chose this sentence in particular because it somehow fits the idea of like how you can sample. So anyone knows what it means? I mean, I have the translation, but do you know what it literally means? You know, das gefällt mir, yeah? It means like it feels good to me, right? It's the way that people say in German, I like it, yeah? They don't say I like it. You can say that, ich mag das. You can say that, but typical thing is that das gefällt mir. That feels good to me, right? Now, this somehow is different in German, the way that you say it, but it's giving you the same concept as I like it, right? But if you want to translate it word by word, it's different, right? Now, if you translate it using a basic translator before neural network, it's going to translate it most probably like, unless it had been like hard-coded inside it, it's going to translate it, it feels to me, right? But it's not a fluent English translation, right? Now, the thing that is happening inside this guy is that this is able to somehow find out that this whole sentence is about that thing is fine to me, right? And then how we can say it natively in English, we say it natively in English, I like it, right? So this is the thing that happens. So the first token gonna be nothing, right? That just start, then you're gonna get the first hidden state, the next token goes in, the next token goes in. Now here, that guy, end of sentence, this guy, is going to say that this sentence is talking about one person, right? That person likes something, right? And it's in present tense, right? Somehow it's capturing all of those features inside it. And that guy now goes inside the decoder. Now, it says, started speaking, so it says, okay, one person likes something, right? And he is the one or she is the one who is speaking, right? And wants to speak in present tense. So the first word should be I, right? So it's going to generate I. And then you might give I also as the input here. You say, I said up to this point I, right? And I'm talking about liking something, and it's in present tense. Okay, the next thing should be like, right? And I like it, right? And then end of sentence because the sentence is over. Does it make sense? So now, what you see here is that the main reason that this guy is not getting into trap of translating word by word is simply because it does not look at single tokens to find the translation, right? It's going to understand what is happening inside the sentence, and it tries to speak natively about that, right? And this is how we translate, right? We don't translate word by word. We just, when we speak multiple languages, we just listen, and we get the idea, then we just transfer the whole idea to the other language, right? And this is what happens here. This is able to do it because it's learning, right? It's not simply following rules, right? It's not a rule-based translator anymore, right? And this is the whole magic happening, right? So the neurons are somehow starting to understand the concepts. How are those concepts? Again, back to the computational world. They are a bunch of numbers. They have no meaning to us. But probably this is the same thing happening in your brain. So there are a bunch of signals which intuitively have no meaning, but they are making your brain to work like that and get the feeling, sensing, right? Everybody's cool? OK, so that's this. But there is one point here, though, OK? And this is the point where you start to see the limitation of this kind of architecture purely based on RNN. The point here is that, well, as I told you, you are every single time computing probability, right? So when this hidden state comes in, right, with the start, it's going to give you one probability, right? So it's going to say that the token I happens with this chance, the token it happens with this chance, the token something else, right, happens with this chance, and so on, right? Now, what you do, you're going to sample or you take the token which has highest probability, for example, right? And now everything is happening by numbers, right? So this might be the case that, I mean, obviously one of the other tokens which is going to have high probability is it, right? Because the language model or the encoder is going to see this, that, well, this is a sentence in present tense starting with das, right? So one other option of translation is that I start my sentence with it in English, right? This is also possible, right? It's, if your language model is trained perfectly, then for this particular sentence, I should happen with higher probability, right? But at the end of the day, it's a limited model, right? It has a bunch of weights. It's going to have a limited capacity, right? So it might happen that, for example, the chance of it happening is very tiny bit more than I, right? And out of the sudden, your language model just samples it instead of I at the output, right? Everybody got the idea? As the first token, right? Because it's true that the language model understands everything inside the original sentence, but it does not look at it as a kind of, well, I am just translating this guy, right? It's going to get sensing about any sentence, right? And because of that, one of the things probably it's going to pay attention to is that it's a German sentence starting with das, which could be corresponding to one English sentence starting with it as well, right? So this is one of the options. Now, if that happens, what we're going to see here? The thing that is going to happen is that, well, maybe we sample it, right, as the first word, right? And then we're going to give it as the second one, right? Now, when you get it, you give this second word, it, into this guy. Now, what's going to be sampled from your language model? Well, your language model is going to say, OK, I said it. No, it doesn't make that I say the second word like, right? It doesn't make sense. It does not relate to the sentence. It's grammatically wrong. So what should I say? I want to be related to the original sentence. And I started with it, so the next one should be fills, right? And this error is going to propagate all over the sentence, right? So it's going to wrongly translate that, right? Simply because it just started with a wrong token, right? If only you would have had it started with I instead of it, then everything would have been right, right? Because this is a language model. It can't speak natively, right? You just needed to tell it just start with I. Please don't do it, right? Everybody sees the problem? Now, if we don't want to build a new thing, do you have any idea how we can prevent this issue? Now, starting with the token I and it could be very close in probability, in chance, right? But if you give the whole sentence, both sentences, I like it, it feels to me. If you give both sentences, which one has higher probability? Which one has higher probability? Do you say too much in English, it feels to me? No, you don't say it, right? In English, you usually say, I like it, right? So the sentence, I like it, happens more likely in English, right? It feels to me happens also because it's not grammatically wrong, but it's not a typical English sentence, right? It's not something that you say every day, right? So this has lower chance, right? So if instead of decoding token by token, I would have had decoded the whole sentence as a whole, right? Then I wouldn't have this problem, right? So maybe I could have the outputs of every single time, right? The row probabilities, right? But I do not sample from them, right? I wait and then I choose among possible sentences, right? Then I'm going to reduce the chance of having this issue, right? So this is the idea that initially people started to do. So initially people, when they were stuck with these RNNs, they started to do this, like basically maximum likelihood sequence decoding. Meaning that it says like, well, I has a high probability, it has a high probability as the first token, right? But this is only the probability of the first token, right? If I multiply the probability of the first token with their consequent, like forthcoming tokens, then I'm going to get two probability of sentences, right? And one of them is much lower than the other one. Then I get the one which has higher probability, right? Everybody's clear? So that was the idea that they started to do. And probably you have here top K beam search. If you have heard of it, you have it on PyTorch also pre-implemented. That is basically a kind of simple implementation of that. So what it does, it basically says that we wait till the sentence is over, and then we just consider all possible combinations, and we take the one which has the highest probability, right? Now, one question. Here I have at the output, let's be simple, 1, 2, 3, 4. I don't care about that. So 4 different words, right? I have 4 different words. And say every single, say my dictionary has 100 words in it. So very simple language, just 100 words, right? 100 tokens, not more than that. How many possible cases you have? How many possible sentences of length 4 you have with a dictionary of length 100? 100 to power 4, right? Because every single word, right? Every single place in the sentence could be one of those 100 words, right? So you have 100 times 100 times 100 and so on, right? So if the sequence goes long, the number of possible cases exponentially goes up, right? And you cannot really do that search, right? So this is the challenge here. So this is, you can do this idea, but this is essentially very computationally complex. So let me write down the idea first. So the idea is to just find the sequence of length L, any length. Say you fix the length even. It's not important. So the one which has the highest probability given the input that you have. How you can write that guy down? Well, you can break it down using chain rule, right? You would say the probability of the first token given the hidden state times probability of the second token given the first token and the hidden state times probability of the third token given the first and second tokens and hidden state and so on, right? Probability of token L given the hidden state that I had and all tokens before, right? I just open it. This is chain rule, right? In probability, not the chain rule in calculus, right? And the base chain rule, right? And then you would say, okay, every single of these probabilities, probability of the first token given anything before, is basically the one that I compute at that particular time by my softmax, right? My first softmax output is giving me the probability of the first token given the German sentence, right? My second softmax is giving me the probability of the second token given the first token and the German sentence, right? The third one is doing the same thing, right? Third token given first and second tokens and the German sentence, and so on, right? So you are going to do that, and basically what you can write is that the output of the softmaxes every single time, you're going to multiply it. But if you want to think about that, well, here I'm just giving you a numerical example, but yeah, just ignore it. It's just confuse you right now. So the thing that is going to happen, you want to somehow find the sequence which has this guy maximum, right? Those multiplications maximum. And as I told you, this is exponentially hard. Now, typically what we do, we usually work with the log likelihood. This means that we are going to compute logarithm of these guys instead of the probabilities themselves. This makes sense, right? If something is maximized, its logarithm is also maximized, right? Doesn't matter, right? So you can take the logarithm. This is going to simplify all the calculations because then it's a sum of log likelihood. So it means that you look at the softmax to compute the logarithm, right? And then you add it up with the next ones, right? But the issue here is that you're going to have as much tokens as you have inside your dictionary to power of L, right? Length of your decoded sequence, right? And this is computationally a nightmare. You cannot afford it. Now, the way that people used to do it is that they are going to do it by K-beam search. Because they would say, it's true I have a lot of choices, right? But many of them do not make sense at all, right? Meaning that their probability is so small that they would never happen, right? They never get the chance to come up as the high probability. I or potato is grammatically wrong. It doesn't have any context. It does not depend on the input, right? So obviously, this is not one choice, right? This is one possible case, right? The first token is I, the second token is R, the last token is potato, right? But it doesn't make sense. This means that the probability is so low that it's not worth that you take a look at it, right? So there are lots of things like that. So there are probably a bunch of them which are valuable. Now, what you can do this idea of top K or K-beam search. So you start with the first token, but you don't take the one which is highest probability. Maybe you set K to be 5, right? So you say that I'm going to take the guys which have, the 5 guys which have high probability, right? Now I go to the next time, right? In the next time, I would say, OK, those 5 guys, I'm going to add them up with all possible cases that I have, right? Now, among them, there are 5 guys again which are having the highest probability of a sequence for length 2, right? I'm going to throw away everything else. I'm going to keep them, right? And I'm going to keep carrying these 5 top guys towards the end. When I am at the end, I'm going to take the highest one, right? So it might be that I has lower probability at the beginning, right? And it has higher probability. But if I keep both of them, then I'm going to check what is the possible case for a sentence of length 2 with high probability. For I, it's going to be I like. For the other one is it feels, right? So I'm going to keep them, and I keep going towards the end, right? And at the end, I have 2 sentences. I like it, it feels to me, right? And I like it has higher probability as compared to it feels to me, right? Even though it was higher probability at the beginning, right? So I'm going to throw that one away. I take the one which has higher probability. This guy is already implemented in PyTorch, and this is the way that people used to do it up to 2017 before attention and transformers become the dominant things, right? So everybody got the idea? What is the problem and how we can somehow resolve it with this basic model? Questions? No question? Yeah.
Like during the RNN, we are having multiple output choices, and in the end we figure out the choices that have the highest joint probability.
Right.
Then we output it.
Yes.
Instead of like output like let's say V1 of V2.
Exactly.
And then we just stack them together and output.
Right.
We have a lot of selections.
Exactly.
Okay.
Yes. Yeah. The best one was that you consider all possible cases and take the one which is the highest joint probability. That's correct, but it's computationally hard, right?
So we choose
Top K, right? You always carry top K in time. So at the end, you're going to remain somehow with K different choices. These are among the choices which have high joint probability, right? And then you take the one which is the highest, right? No. Questions? No question? OK. So if you got no question, then let's get into the next part, which is about attention. So people started to use LSTM to do the translation. It was working. So Google Translate just migrated to natural machine translation, neural machine translation. It became a thing, and then you do not type things in Google, and you see just word-by-word translations anymore. Those embarrassing moments that you just a bunch of students get a placard in some other language, and the native speakers just laugh because they just translated their own language directly by Google Translate. So it was not happening anymore. But the point was that people started to see that if the text is longer and longer, then this translator starts to just work worse and worse, right? So what is the problem here? The problem is that when you have a very long sequence, right, then you're going to process it with your recurrent network. And even if you do the perfect gating and everything at the end of the day, after doing the process, you're going to end up with some feature here, right? And this feature is the only thing that is going to carry from the encoder to the decoder, right? So it doesn't matter how well you design your encoder. At the end of the day, the bottleneck that you're going to see is the guy here, right? So this is the narrowest pipe that is transferring information for you, right? And this is going to dominate the whole process, right? So it has a limited capacity. It can show up to a certain amount of information, right? And the rest of it, it simply just disappears, right? It cannot capture it. And it doesn't matter how, I mean, you might say, OK, let's increase the dimension. Well, you can increase the dimension, but it's not only about dimension, right? It's also about the fact that you are processing it in time, right? When you are processing in time, at the end, you are showing something up which is carrying everything inside the sentence, right? It's easy to get lost, right? So this problem is what we call the information bottleneck. Now, again, I try to make one German to English example. And then I'm not sure if this is the best way to capture it. But the point here is that this is one sentence when you have, ich habe den. This den means the, right? So this one is an article, right? Den Affe, the apple, genommen über den. This den is not the anymore, right? It's actually like which or what, right? It's the other one, right? It's being conjugated in different, say, what is it? Condition inside the sentence, which somehow appears as the article itself, right? Yeah, because of the structure of the German language, right? And now the thing that is going to happen is that both first den and the second den is going to be encoded into the same thing, right? And then this very last vector is going to somehow tell you that there are two dens inside this sentence. One of them is an article. The other one is the connecting word. What do you call what in English? Connecting word? Anyways, it's that word, right? And then that one is just referring to something. This is referring to something else, right? And that information could easily get lost, right? It's a very precise, very delicate kind of distinction, right? That your language model cannot handle anymore. It cannot simply capture out of one hidden stage, right? Everybody's clear? What is the issue? So longer you get, more critical the issue could get, and you might try process it better and better, but it's not going to work perfectly, right? Now, as I said, the whole issue is that you're using a single bottleneck, that red connection that I'm showing there, and this is what we call it information bottleneck problem. There is also a mathematical problem in information theory. We call that one also information bottleneck. Conceptually, they are talking about the same thing, but mathematically, they are different. But at the end of the day, this is, again, the same thing. Like you have anything, any source of information, then you want to transfer it, and then there is a kind of bottleneck which is limited in the capacity that you can transfer information. And that guy is going to just dominate everything. It doesn't matter how well you process it in the encoder, how well you process it in the decoder. There is a kind of physical limitation to the whole process, right? So now, how we can handle this issue? The idea that people started to think about was that maybe we can somehow, if we could use the outputs which we have in time, maybe we can use that to somehow get the idea every single time that we are decoding where we should put our attention inside the input sentence, right? And the problem was initially developed really for the translation, because as I told you last time, translation were somehow treated as a kind of AI complete problem. It was like people had the feeling this is very complicated problem. If we can solve it, we can solve a lot of things, right? And yeah, they really looked into the translation. The original transformer paper was actually talking about the translator. So they wanted to design a translator. They designed it by the architecture only based on attention, and they called it transformer, right? But then gradually it just get its own way to other things. Now, what does it mean? What do I mean by paying attention? It means that when I am going to translate the first token, right? This I, right? If I do have the idea that this token is somehow going to talk about Mia in the English sentence, right? This guy, the last token, right? If I just pay attention to that, then it's going to increase the chance of I simply say I, right? If I want to translate, say I am a very bad translator, right? And I hear this one, das gefällt mir, and I try to translate. If the guy says the sentence and it's over, I might start like, das is it, gefällt is maybe feels, and, yeah? But if somebody just hits me and say, no, pay attention, last word, what was that? Mir, what? I, right? And then everything going to go on, right? So if I can really give attention to this guy in the input, then it's going to increase the chance of translating correctly, right? And that was the idea. How I can do this, maybe I can use the outputs here to somehow build something, right? Build some sort of extra information every time I pass it to my decoder. And decoder, every time that it wants to translate something, it's going to still talk about the context, right, that it received through hidden state. But then it's going to, in addition to that, it's going to pay attention, where should I look in the sentence when I want to put the first token, right? Which word inside the sentence is the most relevant one to what I want to say right now, right? That was the idea. So, yeah, as I said, if you have this attention, so if you do know that you are talking about this last word inside the German sentence, the chance that you get your first output being I, this one is more likely to be I as compared to the case where you do not put any attention, right? You simply talk based on the context that you received. S0 here is what you just encoded by your encoder and gave it to your decoder, right? This is like the second line that you see here is basically what we have done up to this point, right? We just encode, give it to the decoder, right? And the decoder looks at what we encoded, S0, plus start token, it's going to give you the first token, right? But if I give, in addition to that, this attention that, well, you're talking right now, probably you should talk about Mia, right? Not talk about das, right? Then this would just give you it's more likely that it gives you I instead of it, right? Everybody's clear? You can see what I'm talking about, right? Now, and this is what we call the attention mechanism, right? The attention mechanism means that when you are doing decoding, every single time that you want to decode, maybe you can have extra information telling you where you should put your attention inside the encoded sequence, right? And this might help you to improve the quality of your decoding, right? Somehow increasing the capacity, right? Because obviously, you are somehow building new connections, right? You are not only relying on S0, which is passing through the bottleneck, right? You are also connecting your input directly to your output, right? Here you had no connection. Here you are getting the connection, right? And this connection might increase the capacity of transform from encoding to the decoding, right? Everybody's clear? Questions? OK. Now, how we can do it, now, I'm going to explain the attention. Careful, this is not self-attention you use in transformer yet. This is somehow the cross-attention. I have one sequence. I have another sequence. Every time in decoding, I want to pay attention to one token inside my input, right? This is cross-attention, right? And this was the first thing introduced. Later on, people built self-attention based on that, and transformer came, right? So we're going to talk about transformer next Tuesday. But this guy is basically the foundation of that. So when you want to do the attention, every time that you are processing, in addition to the hidden state that you are generating, for that particular time step, x1, for example, right, you're going to also generate one key, right? What is key? Extra features, right? Extra numbers. I put one output layer here, right? One linear layer. I'm going to look at my hidden state. I do some computation. I get one key, right? Now, every time I go on my sequence, I'm going to get new and new keys, right? Key 1, key 2, till key T, the last key, right? So I have all of these keys, right? Everybody's clear? Now, these are just extra computation, extra information I provided. Now, how can I compute the key? We can simply do it by a linear transform. That's a typical thing. So you're going to get your hidden state. You multiply it to a bunch of weights. You get the transform one. You're going to activate it. This is your key, right? This is a classical choice. You can choose the way that you want to do. But this was, I mean, in transformer also, we do everything linearly. OK? Now, you have this one. Now you're decoding. When you get into your decoder, you get your hidden state, right? And first token, now you want to generate, right? You could generate your output token immediately, right? This was the conventional approach. But maybe before we start to speak, we want to just pay a bit of attention, right? What we're going to do, we're going to generate a query. Why we call it query? We're going to say that, OK, we have seen every context, right? Let's take a query, right? This query is going to say some sort of information. What I am supposed to say as the first token when I'm translating, right? That is the query I get on the whole context, right? Now, I have this query, but I can, before I use this query to speak, like to just compute the probability and save my first token, maybe I can compare my query to all the keys that had been inside the encoding, right? So I could say, OK, this query, how much is it relevant to the first token in the encoder, the second token in the encoder, and so on, right? So the thing that we are going to do, we are going to get this query. How we get it? Again, you simply just put one linear layer. You get whatever hidden state you have at that time. You transform it into your query, right? This query is essentially what you used before to start speaking, right? Because you just give it to softmax and you take the maximum probability. But now you don't do that, right? What you do, you get that query, and you start comparing it to every single token inside your encoder. This means that I had, say, t different tokens in my original sentence, right? T different words, right? I'm going to say that this particular token that I want to speak, how much is it relevant to these guys, right? How can I check that relevance? Any idea? One feature, another feature? I mean, it's not something, just any idea? You have two vectors, how you can see whether they are relevant or not? Maybe inner product, right? If inner product is small, then probably they are not relevant. If the inner product is large, maybe they are relevant, right? So what you do, you just compute the inner product of the two things, right? I get this guy. I just compute the inner product. This is the first output. This is just a scalar, a number, right? That number is somehow saying, at this time that I want to decode, how much relevant is the first token when I was encoding, right? I can do it for everybody else, right? So I can compare my query on the whole sequence of the input, right? I could say how much my current token that I'm going to put at the output is going to be relevant to the first guy, second guy, and so on, right? Everybody's clear? So I can compute this one. This is what we call it the inner product vector, or say raw attention, okay? Because somehow this guy is telling you how much attention you should give to every single token inside the input, right? So you want to talk right now, but pay attention. The second and the fifth token inside the input are the more relevant to what you want to say, right? So maybe you build your output based on that connection, right? This is what we call it the raw attention, right? It's raw because it could be any number, right? It could be negative, it could be positive, right? Everybody clear? Now, you have a question? No, they are not activated by same weight. They have independent weights, right? Right. Yeah. No. I mean, obviously they're gonna get, when they are getting trained, they somehow get related, right? But since you are starting from one sequence and you are going to another sequence, which could be naturally different, you cannot use necessarily the same weights, right? So they are independent. They just get trained. Okay. Questions? Okay. Now, the thing that we usually do is that we get this guy, but we have, like, if you look at time L, right, in the decoding, when at this time you're computing your attentions, how much of those attentions you have? T, right? T is the amount of attentions, the number of the tokens inside your input, right? And it makes sense. Every time you're seeing how much attention I should put on every single token, right? And now the next thing that we usually do, we like to just convert it into a probability distribution. How can I do that? I have a vector of size t, which is giving me the attention to everybody, but I'd like to make it look like a probability distribution. What should I do? A softmax, right? I'm going to compute a softmax. Why? Because I like working with probabilities. I would say when it says like 0.2, it means that this guy is 20% relevant. And I make sure that, for example, if two things add up to 0.9, then the rest of them are 0.1, right? So the rest of them are not that relevant. So those numbers, I have feeling about probabilities, right? This is going to help me. So this is what I'm going to do. I'm going to get that guy. So this is a vector, and this vector is generated by comparing your query with every single key that you had inside your encoder. And out of that, you are going to compute a softmax. That softmax is what we call it the attention coefficients, right? The output of the softmax are giving you the attention coefficients. And they are numbers between 0 and 1. They add up to 1. And the one which has higher value is going to give you, it means that that particular token inside your input has more relation to what you want to say right now, right? So maybe you should pay more attention to that. Everybody's clear? So this guy is a probability distribution, definitely. And that guy is going to be somehow tell you that every single token inside your input, how much connection it has to the token that you want to say right now. Right? Clear? Okay. Now, how we can use this attention to speak or to build or token now? Now, one thing that we can do, we can look at the hidden state of every single time, right? So say, for example, it turns out that the second token in the encoder, okay, is very relevant to what you want to say at this time, okay? So you expect this guy going to have a higher attention coefficient, right? Rest of them going to have a smaller attention coefficient, right? Now, if you want to build your output, before this, you would have started with the hidden state at your time, right? But now if you want to somehow build an output which is directly paying attention to this guy. Do you have any choice? Do you have anything that you can use in order to somehow inject more information when you want to generate your next token? What is it? A kind of a skip connection, but what do you need to connect? That's correct, a skip connection. But how do you need to connect? What do you want to connect to your current generated token? What do you use? This K2, this second time step is very relevant. What do you use? You could use K2, right? You can do it, but we don't do it because K we generated for key only, so we don't want to touch it. Maybe H2, right? H2 is the memory at time 2, right? That is the fresh memory about token 2, right? Maybe I can take that guy, right? In addition to what I have. I take that one and also add it to my information, right? But it's hard to find the best one and then you just connect that particular guy, right? And maybe this is the case that the one you want to speak right now, yeah, is related to many things, right? So the best idea is to average everybody, but when you do the averaging using your attention, right? The one which has higher attention gonna get higher weight. The one which has lower attention gonna get lower weight, right? And this would be the idea, right? So you have this probability. You're gonna connect the hidden state at every single time using the attention, right? So you would say H1 is the information fresh at time 1 in the encoding, and I need to pay attention with alpha 1 to it, right? This is the amount of attention I should give to it, so I'm going to multiply that one, right? H2 is the fresh information I got when I was at token 2 in the encoding, and I need to give a very high attention to it, right? Maybe 90%. So I'm going to multiply with 0.9 and add it up, right? And I add everybody up. Those which are not related that much, they are going to get very small attention coefficient. They are going to do nothing. Those which have high attention coefficients, they are going to show up with higher weight and they impact more significantly, right? And I'm somehow making more attention. So the thing that I'm going to do, I'm going to build this attention coefficient, right? So alpha was the attention, this attention variable. Alpha was the attention coefficient that you use, and this A is your attention variable at time L, right? So it's somehow giving you an aggregated form of all attentions you should pay to the inputs, right? Now, you have this guy, right? You already have your hidden state at the time L minus 1, at the time you want to generate, right? Before doing all of this process, you would start from this SL minus 1, right? And you generate your next token, right? But this time you would say, okay, I'm going to get this SL minus 1. I also get my attention, right? I give both of them to the output layer. And then the output layer is going to generate the next token based on the amount of attention I should pay and the memory that I have up to this point, right? So this is the way that you are going to compute your output. So basically what's going to happen at one particular time, you have the memory up to this point, then you can compute this attention, right? I'm showing it with one block, but you do know that inside this block is a query, and it's compared with all the keys, right? And then the softmax has been calculated, the averaging has happened, and you end up with one attention, right? Attention variable. Now you have this attention, you're going to give this attention along with your own hidden state in order to compute your output. Everybody's clear? Questions? So this extra attention is going to help you a lot because somehow if there is one obvious part inside your encoding that you need to pay attention, this is going to get significantly high weight and this is going to impact your output generation, right?